Water, 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 drip, water, splash, water.
Welcome to my edition of Draw My Life. It's me, water. Some people like to call me H2O. I'm the most abundant substance in living systems, and I make up around 70% or more of most organisms' weight. The first living organisms arose in an aqueous environment. Most all biological molecules assume their shape in response to me. I make up 60% of humans. This is me. I'm a molecule that's super tiny, but up close this is my makeup. I am 2 hydrogen atoms that are my positive features and 1 oxygen that's my negative charge. I have these dashed lines that are non-bonding orbitals. They're just some extra electrical support. I get hot pretty easily. My melting point is 0 degrees Celsius. It takes 100 degrees to get me boiling, and my heat of vaporization point is about 2,260 joules per gram. I identify as a polar solvent. I am polar because I have a slight imbalance of electrical charge in my structure, since my oxygen atoms are more electronegative than my hydrogen atoms, meaning they try to pull the electrons closer to themselves. And I am a solvent because I am a liquid that can dissolve solids, hence the name polar solvent. I can readily dissolve most biomolecules, which are generally charged or polar compounds, or in other words, compounds that love me and go by the name of hydrophilic. However, there's a group of nonpolar molecules called hydrophobic that don't interact well with me. Like for example, oils and fats. We just don't get along and don't mix well. And then there's amphiphatic molecules. It's a love-hate relationship. With other molecules of water, there are hydrogen bonds. This is a weak interaction between an oxygen atom of one molecule and the hydrogen of another. Water molecules are in a tetrahedral arrangement. My oxygen atom is more electronegative than the hydrogen ones, so the sharing of my electrons is unequal and atoms become 2 dipoles. These hydrogen bonds between molecules of water provide cohesive forces that make me liquid at room temperature and a highly ordered arrangement of molecules at cold temperatures. People call me ice when I look like that. When I'm cold, I'm way less dense and I have 3 hydrogen bonds. My polar biomolecule friends dissolve really easily when we hang out because they're more energetically favorable than water molecules, and they can replace the water-to-water interactions that I already have. In liquid form, I have around 3.4 hydrogen bonds with other water molecules. Sometimes the hydrogen bonds I have aren't between other water molecules, but with some polar solutes. These bonds are formed between 2 molecules. One is a hydrogen acceptor and the other one is a hydrogen donor. I can do both donating and accepting depending on the molecule that the polar solute is made of. I'll show you what I mean. Here is me being a donor. I am using my hydrogen to bond with an oxygen from this carbonyl group molecule. And here I am an acceptor. I'm accepting a bond from the hydrogen from this peptide group using my oxygen. So, when are hydrogen bonds the strongest? Hydrogen bonds are strongest when the 3 atoms involved lie in a straight line, which means that the acceptor atom is in line with the covalent bond between the donor atom and hydrogen. As a solvent, I can dissolve many crystalline salts by hydrating their ions. For example, the salt sodium chloride is always assembled in a crystal lattice. I can disrupt this structure by hydrating and stabilizing the sodium and chloride ions by clustering around them. My oxygen atoms are attracted to the positively charged sodium ions and my hydrogen atoms to the negatively charged chloride ions. This interaction neutralizes our joint ionic charges
and weakens the electrostatic attractions necessary for the salt crystal lattice formation.
Let me try and explain this van der Waals thing to you. It's a type of interaction that I'm capable of. See, this is two simple atoms of water. If they become too close, something around 5 nanometers, forces are driven by induced electrical interactions between two or more atoms or molecules, and the atoms are slightly distorted, for lack of better words. It's a distance-dependent interaction, and if they aren't too close, they're fine, but when they're close, they are attractive or repulsive.
So about that group of amphipathic compounds, most of the time they're phospholipids, like the ones in cell membranes. Since phospholipids have a hydrophilic head and a hydrophobic fatty acid tail, when mixed with water, the lipid chains become surrounded by a layer of highly ordered water molecules. Next, as the lipid molecules cluster together, only the lipid portions at the edge of the cluster force the ordering of my molecules. In the next step, all the hydrophobic tails are sequestered from me, as the phospholipids cluster in a sphere to form micelles. The ordered shell of my molecules are therefore minimized. The energy that is gained by freeing my immobilized molecules stabilize the micelles.
Water, yeah, water, yeah, water, water, okay, water, what, water, drip, water, splash, water.